Welcome to the ExaLINK Fusion introductory video. In this video, we will discuss the basic principles of operation and configuration for the ExaLINK Fusion product series. Full documentation for all of the topics covered can be found at fusion.exablaze.com. Additionally, at the bottom of each slide is a link to further relevant information for the contents of that slide. To begin with, we will discuss the architecture of the ExaLINK Fusion product series. The ExaLINK Fusion is a modular platform that can be configured in a number of different ways. It can operate as a layer 1 matrix switch, which provides low latency tapping, patching, and monitoring function in a 1-to-n manner. It can also implement layer 2 multiplexing functions, such as low latency connection aggregation, in an n-to-1 manner. The device can also operate as a complete layer 2 switch in addition to the functions previously described. Finally, the device can also operate as a complete network application platform, including programmable FPGA and optional x86 modules. Internally, the device is segmented into three major regions: the front panel, the layer 1 crosspoint, and two optional module bays. The front panel can be populated with up to 3 line cards. Each line card provides up to 16 10 gigabit per second Ethernet connections or 4 40 gigabit per second Ethernet connections. The line cards are designated A, B, and C. The device is available in 16, 32, and 48 port configurations. It's important to note that there is no internal distinction between the line card bays. Connections between line cards can be freely made, and there is no penalty for this. The front panel is connected to the layer 1 crosspoint device. A layer 1 crosspoint is an electrical-only device that allows connections in a 1-to-n manner between all of its ports. The device is not aware of packets, and is the reason that we can implement very low latency functions such as tapping, patching, and monitoring. The layer 1 crosspoint device is also connected to 2 internal module bays. These module bays can be optionally populated to provide higher layer functions such as multiplexing and layer 2 and 3 switching operations, as well as an x86 CPU. The device is available without module bays in a layer 1 only configuration. It can also be provided with a single FPGA module to implement layer 2 multiplexing and switching operations. It can be provided with 2 FPGA modules, where the second FPGA is available for user custom applications. And finally, it can be provided with an FPGA module and an x86 module, both for user custom applications. Because the device is FPGA based, it can be configured with multiple different firmware modes. At current, the device supports 3 different firmware modes. These are Fast Mux, Mux, and Switch modes. The Fast Mux is a minimally featured, low-latency multiplexing firmware mode. It can perform muxing in as little as 39 nanoseconds. The Mux mode has a higher degree of features, including 1G support, as well as VLAN tagging and trunking. The Switch mode includes a complete Layer 2 switch. Both Switch mode and Mux mode support tap aggregation and timestamping. For full details on the differences between the firmware modes, please see the documentation. Throughout the rest of this presentation, I will include a simplified version of this architectural diagram in the bottom left-hand corner of each slide. This diagram will give an idea of the physical components that are currently in use for each example. Before we proceed with the examples, it's helpful to have a quick introduction to the Fusion command line interface. There are several ways to log into the device. The most common are through a serial connection or through an SSH connection. In this example, I am connecting via SSH using the default username admin and the default password also admin. As I log in, I'm placed into Inspect Settings mode. In this mode, I can inspect settings of the device, but I cannot change them. To navigate around the device, I can use tab completion, which will complete commands that are partially completed, but also provide suggestions for commands when I don't know what the correct command is. I can also use question mark to provide more detailed help. In order to make changes, I need to enter the configuration mode. I do this by typing conf and optionally tabbing to complete to configuration. In configuration mode, I can now modify settings of the device. I can exit this mode by typing X or exit with the tab completion, and I'll be back to the inspect settings mode. As with other similar devices, I can also apply modeless configuration, where I use the command configure and then, for example, port A and any other things needed to complete that command. This should give a fair sense of how to drive the command line interface. As we progress, we're going to be using the following demonstration configuration. In this configuration, we have an ExaLINK Fusion and 4 hosts, hosts 1 through to 4, connected onto line card B on ports B9 through to B12. The simplest operation to perform on an ExaLINK Fusion is to create a layer 1 patch. This is an electrical layer connection that connects 2 ports to each other directly. In some ways, it's similar to using a direct attach cable as shown in the diagram. You can see from the architectural diagram on the bottom left-hand corner that we're using only the line card bays and the layer 1 module. In practice, a layer 1 connection might connect hosts 1 and 2 through ports B9 and B10. To configure this on the command line, we would enter configuration mode or perform modeless configuration. In this case, we have a modeless configuration, configure, patch, ports B9 to port B10. And you can see that the device responds by saying that the patch has been created. Very similar to a layer 1 patch is a layer 1 tap. Layer 1 taps are often used for monitoring, and in this way they're very similar to an optical splitter device. In this example, we might want to monitor both sides of the patch that we created in the last example. The physical manifestation would look something like this. We add a tap to port B9 and send it to port B11, and also tap to port B10 and send that to port B12. On the command line, this is very similar to creating a patch. In this case, we've entered configuration mode by using the command configure, and then we've created a tap by using the command tap B9 to B11, and the device has responded by saying that a tap has been created. Similarly, we'd do the same to ports B10 and B12, and we can then exit using the exit function. One of the other common uses for layer 1 tapping is low latency fan-out. This is where we need to share data from one source to many destinations. For example, a trading exchange might produce market data that needs to be shared with many trading servers at very low latency. Configuring this on the command line is the same as configuring taps in the example as previously given. The final major feature of the layer 1 mode of the Fusion device is its statistics and packet dump features. The device can provide overview statistics, including statistics for all ports, up-down status, alias names, and so on. It can also provide detailed statistics for each port, including signal quality, packet and error counts, SFP information, and so on. Those statistics can be reset, and the device can also provide live packet dumps. To obtain overview statistics is quite easy. Simply issue the show port command, and note that this does not need to be done in configuration mode. To obtain detailed statistics, use the same command, but this time supply a port. In this case, show port B9. The result of this command is very detailed statistics about the given port. In this example, you can see the link up-down status, the packets and bytes received, errors, and other information such as the signal strength. To reset the counters, you will need to enter configuration mode, in this case configure port B9, and then add reset counters, and the device will respond that the counters have been reset. All counters will then be reset to 0. For debugging purposes, it's often useful to have packet dumps to inspect the packets that are currently on the wire. Packet dumps can be performed from the inspect settings mode using the port command, in this case port B9, and the command packet dump. Packets are provided in hex format, allowing you to easily read the contents of those packets. In the discussion so far, we've focused on how to create objects in the Fusion, such as patches and taps, but not how to remove them. Objects are removed in much the same way as they are created. However, the command is prepended with the keyword no. So for example, if we wanted to remove the tap between ports B9 and B11, we would enter configure mode and we would issue the command no tap B9 B11. Similarly, to remove the patch between ports B9 and B10, we enter the command no patch B9 B10. Similar commands are of course available for other objects such as muxes and switches. In the previous example, we used two tap objects in order to inspect the traffic that was flowing between ports B9 and B10. This is certainly a useful way to monitor traffic, but we may wish to use a single monitoring port so that we can monitor traffic on a single capturing device. To do this, what we would need to do is aggregate the traffic going out of that port. The Fusion supports an object type called a mirror, which in other devices is called a tap-ag device. In this example, we create a mirror which has an output on port B12, and we add ports B9 and B10 as inputs to that mirror device. To create a mirror object, we enter configure mode, and we give the mirror object a name by using the mirror and then followed by the name command. In this case, I've used the name myMirror. The device responds that the mirror has been created. We can then set an output port by using the keyword output, followed by the port that we wish to output to, and the device will similarly respond. And we can then add ports that we wish to mirror as inputs using the port command. Finally, we can use the show command to show the configuration of that mirror, and it will show the current settings for it. As usual, we can exit this using the exit command. When monitoring traffic in a network, it's often useful to apply timestamps so that we know the exact order that network events occurred in. The mirror object supports this and has very high resolution timestamps with synchronization to PTP, PPS, and GPS. The physical realization of a mirror with timestamping is identical to the previous mirror, except that we have now applied timestamping. To configure a mirror with timestamping, we enter configure mode with the mirror name, and we simply set the timestamp mode. In this case, we've set the timestamp mode as append. There are currently 4 supported timestamp modes, 2 Arista-compatible timestamp modes, and 2 Exablaze specific timestamp modes. One of the most common use cases for the ExaLINK Fusion device is as a multiplexer that multiplexes many connections into a single high-value connection, especially where this needs to be performed at very low latency. For example, consider a scenario in which multiple trading servers need to connect to a single trading exchange. Multiplexing is performed in all of the 3 current firmware modes. These firmware modes are the fast mux mode, the switch mode, and the mux mode. Each of these modes has a different sets of features, which results in different latencies. The simplest multiplexing mode is called the raw mux mode. In this mode, packets are multiplexed through the FPGA in the upstream direction from the many servers up to the one connection point, but on the return path, packets are simply distributed through the layer 1 device, resulting in very low latency. The lowest multiplexer latency is slightly under 40 nanoseconds, and the lowest return latency is a little under 5 nanoseconds, giving around a 45 nanosecond round trip through the device. In our demonstration setup, we have applied a multiplexer to ports B9 and B10, multiplexing into port B11, but at the same time we continue to monitor ports B9 and B10 and aggregate them through a timestamping mirror out of port B12. Creating a multiplexer is very similar to creating a mirror. We enter configure mode and give the multiplexer a name, in this case myMux. We can then add ports, in this case ports B9 and B10, and the device will report that the ports have been added. We can then set an upstream port, which is the port connected to the single connection, for example the exchange, by adding port and specifying that it is an upstream. Similar to the mirror, we can use the show command to show the settings of the device. There are some situations in which using a layer 1 device for spraying the packets on the return path is not suitable. In these cases, multiple clients may be listening and we do not want packets to be confused between the different clients. In this case, we have what's called a layer 2 mux or L2 mux. The L2 mux performs packet inspection and directs packets based on the destination MAC address to the correct client. This requires that packets go through the FPGA, which increases the latency. Also note that the L2 mux is not supported in the fast mux firmware mode. Switching from a raw mux to an L2 mux is straightforward. We enter configuration of the mux as usual using the command config mux and the mux name, in this case myMux, and then we set the mode to the desired mode, in this case layer 2. Again, we can use the show command to show that this change has been applied. In addition to muxes and mirrors, the Fusion device also supports complete Layer 2 switches, and depending on the firmware mode, these can also be instantiated at the same time as other objects. In this example, I've extended our demonstration configuration to have 4 more hosts, host 5 through to host 8, connected to Module Bay A. You can see that the hosts are connected on ports A1 through to A4. To create a switch on the command line is very similar to creating mux and mirror objects. We enter the configuration mode and we give the switch a name, in this case MySwitch, and we add ports to the switch using the port command, in this case port A1, A2, A3 and A4. As usual, the device responds that the ports have been added. Similarly to a mux, we can use the show command to show the current status of the switch. Switches, muxes and mirrors all have many further settings and features, including VLAN tagging and trunking and MAC learning. Please see the documentation for more details on these. From all of us here at Exablaze, we hope that you found this brief introduction to the ExaLINK Fusion series to be useful and informative. If you have any further questions, please do not hesitate to reach us through our support channels. My name is Dr. Matthew Grosvenor, and I've been speaking on behalf of the team at Exablaze.